Welcome back to another powerful episode of the Change Dude podcast, where we dive into game-changing ideas, disruptive innovations, and the stories shaping our digital world. I'm your host Saeed Rafay, and today we are stepping out of the realm of classic bits and entering a universe that defies conventional logic. A universe where particles can be in multiple places at once, where computation isn't limited by binary choices, and where the possibilities and risks are staggering. The universe is quantum computing. This episode is all about exploring the promise and perils of quantum computing. And I promise you, it's not just about qubits or Schrodinger's cat. It's about how this technology could reshape everything from drug discovery to national security, from artificial intelligence to financial modeling, from breaking encryption to redefining creativity. Quantum computing isn't just the next big thing. It could be the final leap before we unlock an entirely new layer of reality. But like any leap, it involves risk, and we need to understand both the opportunity and the threat if we want to steer our future responsibly. So buckle in. Whether you are a curious mind, a tech enthusiast, a policymaker, or just someone wondering what all this quantum fuss is about, this episode is for you. Quantum computer is more than a faster computer. It's a different kind of computer. To understand it, let's briefly compare it to the classical computers we use every day. The ones powering your smartphone, laptop, or this very podcast. Classical computers operate using bits, ones and zeros. These are like tiny switches that are either on or off. By stringing billions of these bits together, we can perform everything from a simple Google search to training a large AI model. But quantum computing throws that rulebook out the window. Instead of bits, it uses qubits or quantum bits, which can exist not just in a state of 0 or 1, but in a superposition of both. It's as if every qubit is simultaneously trying out every possible combination of 0 and 1 until it collapses into one value when observed. What does this mean in practice? It means that quantum computers can, in theory, process certain kinds of problems exponentially faster than classical computers. Problems so complex that even the fastest supercomputers in the world would take millennia to solve. Now this isn't magic, it's physics, specifically quantum physics. The very nature of matter at the smallest scales allows us to exploit phenomena like entanglement and tunneling, enabling quantum computers to calculate across massive probabilities instead of grinding through linear logic. But there is a catch, a big one. Qubits are incredibly fragile. They decohere or fall out of their quantum state from the slightest environmental disturbance, a fluctuation in temperature, a stray electromagnetic wave, even cosmic rays. That's why building a working quantum computer is so insanely difficult. And yet, that's precisely what companies like IBM, Google, Intel, and startups like Rigetti and PsiQuantum are racing to do. Let's take a moment to understand the science that powers quantum computing. It starts with superposition, a concept so bizarre that Einstein himself struggled with it. A classical bit is like a coin that's either heads or tails. A quantum bit is like a spinning coin that's both heads and tails at the same time until you stop it and look. Superposition allows quantum computers to explore multiple outcomes simultaneously. If a classical computer has to check every combination in a password one at a time, quantum computer could in principle check all possibilities at once. Then there is entanglement, a phenomenon where two qubits become inextricably linked. Change one and the other changes instantly, no matter how far apart they are. Einstein called it spooky action at a distance. For quantum computing, this means that information can be shared and coordinated across vast networks of qubits without direct interaction. It's like having a psychic link between the parts of your processor. Finally, quantum interference helps in amplifying the probabilities of correct answers and cancelling out the wrong ones. Imagine thousands of paths converging, interfering with each other like ripples in a pond. Through this interference, a quantum computer zeroes in on the most likely correct results. The principles aren't easy to wrap your head around. They defy our classical intuition. But they are not fiction. They have been observed in the lab again and again. Quantum computing simply dares to build machines that use these rules rather than fight them. If understanding quantum theory is mind-bending, building a quantum computer is even more so. Imagine a machine that must operate near absolute zero, colder than outer space, because any heat would collapse the fragile quantum state. These computers must be shielded from noise, vibration, and radiation. The slightest hiccup can introduce quantum error, rendering calculations useless. This is why most quantum computers today are confined to ultra-controlled labs and resemble sci-fi machinery more than a MacBook. Their processors are often suspended inside dilution refrigerators, massive cylindrical cooling units that create the coldest environments on Earth. Moreover, qubits themselves are made from exotic materials, superconducting circuits, tapped ions, photons, and even topological structures that don't yet fully exist in reality. Each approach has its strengths and limitations, but none has yet cracked the code of large-scale, fault-tolerant, general-purpose quantum computing. So today we are in NISQ era, which stands for Noisy Intermediate Scale Quantum, where quantum machines have been between 50 and a few hundred qubits, enough to do some cool demonstrations, but not yet to solve useful problems better than classical computers. Yet, progress is accelerating. IBM has published roadmaps. Google achieved a milestone called quantum supremacy by performing a task their Sycamore processor completed in 200 seconds that would take 10,000 years for a classical machine. Still, critics debate how meaningful this really was. Quantum hardware is evolving, but so far, the quantum leap remains just out of reach. A computer without software is useless, and quantum computers are no different. The difference is that quantum software doesn't just optimize, it redefines. At the heart of this revolution are quantum algorithms, mathematical recipes that can exploit quantum properties. The most famous is Shor's algorithm, which can factor large numbers exponentially faster than classical algorithms. This threatens to break RSA encryption, the very foundation of today's secure internet. If quantum computers ever reach sufficient scale, most existing encryption would instantly become obsolete. Another powerful tool is Grover's algorithm, which speeds up unsorted database searches. Then we have quantum machine learning, quantum simulation, and quantum optimization. These are early fields but promising. Imagine training neural networks in seconds instead of weeks, or simulating every interaction of a molecule to find the perfect drug compound. But writing quantum software is hard. It's not just Python with a twist. It requires a new mental model, a blend of logic, physics, and probability. New quantum programming languages like Q#, Qiskit, and Cirq are emerging, and a whole generation of developers is slowly learning this new art form. And it is an art form, one that could soon redefine what it means to solve a problem. Let's talk about the elephant in the room. Quantum computing isn't just a scientific quest, it's a geopolitical arms race. Governments know that whoever wins quantum supremacy will have a massive edge, economically, militarily, and digitally. The US has invested billions. China is reportedly ahead in some areas, building national quantum networks and military applications. The European Union and India are racing too, alongside private giants like IBM, Google, Microsoft, and Amazon. So why such urgency? Because quantum computers could break public key cryptography, rendering current digital security useless. This isn't just about your WhatsApp chats. It's about military secrets, bank records, infrastructure controls, and even the digital backbone of democracy. Quantum technology is also a new class of weapon. Just like nuclear tech changed warfare, quantum could change cyber warfare. And with that, the stakes couldn't be higher. There is also economic power at play. Countries and companies that harness quantum capabilities will dominate finance, pharma, logistics, artificial intelligence, and material science. Quantum could unlock new sources of energy, create super optimized supply chains, or design drugs no classical simulation could predict. It's no longer a question of if quantum computing will arrive. It's a question of who will wield it first and for what purpose. So let's shift from the fear to the promise. Because quantum isn't just a threat, it's also the most powerful hope for solving problems that have stumped us for decades. In pharmaceutical, quantum simulations can predict how molecules will behave, revolutionizing drug discovery and potentially eliminating years of trial and error. We could design custom cancer treatments, antiviral compounds, or entirely new classes of medicine tailored to human biology. In climate science, quantum computers could simulate atmospheric chemistry to model carbon capture more effectively, or design materials that revolutionize batteries, solar panels, or clean energy storage. In finance, they could model complex market scenarios and optimize portfolios in ways that classical computers cannot. In artificial intelligence, they could supercharge model training and discovery. Even in materials science, quantum computing can help design superconductors that work at room temperature, potentially unlocking lossless power grids and quantum internet. The impact could be revolutionary, not incrementally better, but orders of magnitude beyond what we thought was possible. And yet, the same power that can heal can also harm. Quantum computers will widen the gap between quantum haves and quantum have-nots. If only a handful of companies or countries control this power, the digital divide could become irreversible. There is also the security dilemma. Do you reveal that you have cracked an enemy's encryption, or keep it a secret and watch silently? Ethics in quantum espionage are uncharted territory. Then there is the fear of unintended consequences. Imagine releasing a quantum AI that can rewrite itself exponentially fast, or a black hat quantum hacker who exploits a vulnerability no one else can even detect. Like nuclear fission, quantum is dual use. It can light cities or level them. It can cure diseases or destabilize nations. And once it is out of the box, we won't be able to put it back. That is why quantum ethics and quantum governance are becoming critical areas of discussion. And it is why we need public awareness, open research, and international frameworks before we rush headfirst into this brave new world. We are still early. Despite all the headlines, quantum computers today are not yet powerful enough to outperform classical ones in most real-world tasks. Maybe 5, 10, or even 20 years away from real quantum breakthroughs. Yet, the progress is undeniable. Every year, quantum hardware gets more stable. Every year, new algorithms emerge. Every year, more talent pours into the field. The next decade will likely mirror the early days of the internet, full of uncertainty, hype, and bold predictions, many of which won't pan out. But some will, and those few will change everything. We will also see new industries arise: quantum cloud platforms, quantum cybersecurity, quantum sensors. New careers will form, from quantum ethicists to quantum UX designers. This isn't just a technical revolution, it's a societal one. But make no mistake, the hype must be balanced with humility. Quantum computing won't solve every problem. It is not magic, but it might just solve the ones we thought were impossible. So where does that leave us? Quantum computing isn't just a technological shift, it's a physical one. It challenges our assumptions about reality, computation, even causality. It invites us to think probabilistically, to compute across dimensions, to dream on a scale never before imagined. But with that dream comes danger, ethical, economic, and existential. We stand on the edge of quantum leap. What we do now, how we build, govern, and distribute this technology will shape the course of human history. As listeners of the Change Dude podcast, I know you are already forward thinkers. So stay curious, stay informed, ask tough questions, and most of all, stay human in the face of overwhelming machine power. Because the real leap, the one that matters, is not in qubits or circuits, it's in consciousness, in compassion, in the choices we make. Until next time, this is Saeed Rafay signing off from the Change Dude podcast. Keep questioning, keep changing.